So what we're going to talk about today is the idea of something being more likely dependent on another event having already taken place. And we're working towards the idea of determining whether or not two events are independent, which we'll talk about on Friday. But today, before we can do that, we really need to iron out the idea of how to calculate the probability of one event given that another event has happened. So for example, generally speaking, if I want the probability of event A given that event B has happened already, I use this bar to indicate that that's what I'm looking for. And so what that means is, what is the probability that A is going to happen if we assume that B has already happened? So the way that we calculate that is we think about the fact that since B has already happened, that changes our number of possible outcomes to be only the B events. If it's given that B has happened, then we're only talking about the situations where B has happened. So now, of all of the times that B has taken place, how many of them also included A? And so the way that we write that is, what's the probability of A and B occurring together, which is the intersection of the two events. So this is a formula that we've used in the past in Algebra 2, and it's a formula we're going to use today. So let's take the example of the people with the shoes and the hats and the dresses and calculate some of these conditional probabilities. So this first example here says calculate the probability of someone having blue shoes given that they have a red hat on. So we'll use this formula that we've constructed here. And remember, that means that our denominator is going to be the probability of someone having a red hat. And our numerator is going to be the probability that someone has blue shoes and a red hat. And I won't be using colors the whole time, but I think initially it's helpful. Okay, so where are the people who both have blue shoes and have a red hat? So that's just this guy. He's the only one who has a red hat and blue shoes. So there is only one person here who meets that criteria. And then I need the probability that someone has a red hat. So how many people have red hats? 2 of them. So 1/2 then is my probability. And let's think about this logically. If we wanted the probability that someone has blue shoes given that they have a red hat, we're only considering the red-hatted people. And of those 2 red-hatted people, how many of them have blue shoes? Just the 1. All right, let's take example 2. The probability that someone has a red hat given that they're wearing a green dress. So how many green dresses do we have? We've got 1, 2, 3 green dresses, so that's my denominator. And of the green dresses, how many of them also have red hats? 1. So the probability of someone wearing a red dress, a red hat, given that they have a green dress on, is 1/3. And something to keep in mind is that in the previous video, we determined that the probability of someone wearing a red hat, just all by itself, was 1/5. So this is something to think about. Clearly, the probability that someone is wearing a red hat is higher if we're only picking from people who wear green dresses than it is if we're picking from the whole group. So this isn't something we're considering necessarily today, but think about the fact that the probability of picking a red-hatted person went up once we limited our scope to only people in green dresses. That means something. All right, so number 3. What's the probability of picking someone who's wearing blue shoes given that they're wearing a green dress? There are 3 people with green dresses, and how many of them have blue shoes? None of them. So that is a 0. There are no people who are wearing blue shoes and have a green dress. And the last example. What's the probability of picking someone who has a red hat given that they are not wearing blue shoes? Okay, so that's the complement of set B. So our denominator is going to be the number of people who are not wearing blue shoes. That's 1, 2, 3, 4, 5, 6. 6 people do not have blue shoes on. And of those 6 people, so I'm not talking about people who have blue shoes anymore. Of these people, how many of them have red hats? 1 of them. So 1 in 6. All right, let's look at data in a table. So here we've got a table of data where clearly we had a bunch of people who were surveyed. We've got dog people, we've got cat people, we've got adults and children, and it's always a good idea to make a total of how many people we're dealing with here. So it looks like if I add up the adults, I have 28 28 adults, and children, there are 32 children. So that should give me a grand total of 60 people. Let's make sure that it works the other way. Dog people, there are 38 of them. Cat people, there are 22 of them. That also adds up to 60 people. So a total of 60. Let's calculate the following probabilities. What is the probability that somebody is a, K denotes child here, a child given that they're a dog person? So again, our denominator is going to be the number of dog people. How many dog people are there? 38 total dog people. And of those 38 dog people, how many of them are also children? Just these 25. This is a good example of where you would not want to turn your answer into a decimal, because this is not an exact decimal. So you're going to want to leave your answer as a fraction. What's the probability that somebody is a cat person given that they are an adult? So of all the adults, of which there are 28, how many of them are also cat people? So of these 28 adults, we have 15 cat people. So 15 28ths. What's the probability that someone is a dog person given that they are a child? Okay, so our denominator is the number of children. There are 32 children, and of those 32 children, 25 of them are dog people. And then finally, what's the probability that someone is an adult given that they are a dog person? So of all the dog people, how many of them are adults? And so this is what you're doing when you go through the practice. You're going to go through the same process. So our probabilities are not quite as straightforward as they used to be. We're no longer working from the total number of people. It's now restricted to whatever is given. So your denominator in all of these situations is going to be that B event, or the second event that's taking place.